Bismillahirrahmanirrahim. Today we will discuss components of gradient of vector v and its divergence of vector, divergence of tensor, curl of vector in polar coordinates. We will discuss first all of these in polar coordinates. Then after this we will discuss all these things in cylindrical coordinates. In previous lecture we have started polar coordinates and we have discussed the gradient of any scalar function f in polar coordinates. Let us start components of gradient of vector v. Suppose that we have a vector valued function given in equation number 1 in polar coordinates. V of r theta equals to Vr r theta Er plus V theta r theta E theta. It has two components, so there would be total 4 components for gradient of vector v. First, second, third, fourth. Now we have to find these 4 components, and we know that gradient of v is a tensor, so when we will apply this tensor on this vector we will have this thing. We will have dv, differential f. This is coming from the definition of gradient of vector. Let us suppose that we denote this gradient of v with this tensor t, so we can write dv t dr. Instead of this we have t. No, you know that what is dr. This is from your previous lecture. Dr is dr er plus r d theta e theta, where you have the differential of r. And you know that t is tensor, so you have equation number 2. It will be outside ter plus r d theta d e theta. Now what is d er and what is d e theta? D e r equals to, this is coming from your second lecture of continuum mechanics. The TE1 was written as TE1 equals to T11 E1 plus T21 E2. Now here we have, where we have coordinates x1, x2, x3, here we have r theta, and it means that T of er equals to TRR instead of T11, and instead of E1 here we have ER plus, there was T21 second, T21, 2 was the x2, 2 is coming from x2. Here second coordinate is theta, so theta will be at the first position, T theta r, because we have coordinates r theta. Yeah. And with E theta, here we have T12, Tr theta Er plus T theta theta E theta. Use these two in equation number 2. We have this, we have written this v in terms in linear combination of Er and E theta. We have combined the coefficient of Er here, coefficient of E theta. We have equation number 3. This differential of v is coming from the definition of gradient of v. No, what is What does calculus say about the differential of v? This is from the definition of gradient, with the help of definition of gradient of vector v. Now this is the basic definition of the differential. That's how we define the differential of any function. We know that v is given in equation 1, then we will take the differential dv equals to dv of v or er plus dv theta e theta, as d is linear, differential is linear, so we can write this. Now we will open the differential of er plus vr as it is, differential of er plus d of v theta e theta as it is, plus v theta d of e theta. We know that what is the value of this and this. What is d of differential of vr r theta? As vr as function of r theta, then with the help of definition we can write partial v partial r dr plus partial vr partial theta d theta partial dv theta r theta, this one is equal to partial v theta r dr plus partial v theta theta d theta. And we know that what is d of er, differential of er is d theta e theta, differential of e theta is minus time d theta er. Now we will use these in equation number 4, and we have this. After rearranging, we have equation number 5. Here we have coefficient of er is this, and here coefficient of e theta is this. Now with the help of calculus, we have differential of v as equation number 5, and with the help of our definition of gradient, we have differential of v given in equation number 3. So both the differential must be same. Then from 3 and 5, 3 and 5 we can have this thing. On left side we have dv for both equation, then on right side we will compare the coefficients of er e theta, or the coefficient will be 0. Then by comparison er and e theta, moreover you can see that here we have dr, d theta, dr and d theta, and here also we have dr, d theta, dr and d theta. When we compare coefficients of er and e theta, we have this equal to this. After that we can see that here we have dr, it will be compared with this dr. Sorry, okay, this dr, and here we have d theta, this will be compared with this rt r theta, because here coefficient of d theta is rt r theta. Similarly from second term of 3 and 5, trr equals to v partial vr partial r, and tr theta equals to this divided by r. Similarly t theta r and t theta theta. Now these are the 4 components which we have required from our start: del v r, del v r theta, del v theta, del v theta theta. First component, second, third and fourth. This is the form of gradient of vector v in terms of polar coordinates. No, the divergence of V. We have defined the divergence of V as a trace of this matrix. As trace of this matrix. You can see this thing from your discussion in Cartesian components. Rectangular Cartesian components. So what is the trace of del V RR plus del V theta theta? Now when you sum these two elements, you have equation number 6. This is the divergence of vector V in terms of polar coordinates. And if you have V in terms of Cartesian, then you have simple partial Vn, partial x1 plus partial V2, partial x2 plus partial V3, partial x3. Now if your vector V is written in terms of polar coordinates, then divergence of that vector V would be in this form. You have some derivatives, partial V R plus 1 over R into partial V theta theta plus VR. Equation number 6. Now curl of V, as we have defined curl of V as that curl of any vector V is equal to 2 times the dual vector of antisymmetric part of that vector. This is what we have defined in our Cartesian components. So definition will not change, that will remain same. So curl of V will also be equal to here 2 times dual vector of this antisymmetric part of gradient of vector V. So first we have to find gradient of antisymmetric part of gradient of vector V. This is very simple because we have only 2 by 2 matrix. So this will be 0, final form. This will be 0, and here will be simply by formula del V antisymmetric equals to del V minus transpose of del V divided by 2. If you take the transpose, then we have this minus this second, and here this minus this the first, and diagonal will be 0. Now here we have divergence. You have divergence of V, curl. And now you can have this thing from your formula. Coefficients of E1, E2 will be 0 because they are involving either third component or with respect to derivative of third, and they are 0. We don't have third, so the first two will be 0. We have only one component for curl of vector V. Simply we have T, this would be T2 1, and we have this T2 1 into E3. No components of divergence of tensor. We know the divergence of T is a vector, and by the definition we can write this equation. The divergence of T will satisfy this type of equation, that when you will take the derivative dot product of that divergence of T, that vector with any vector A, then you will have this thing on your right hand side. Result would be this. For any arbitrary vector A. Now here we have two components of this divergence. One is R rth component and theta component. Now to find r component in similar fashion, that if you have vector v and you have to find the first vector v, first component v1 of that vector, then what you will do, you will take simply the dot product of that vector with e1, dot product of v with e1, v dot e1 equals to v1. Similarly here, if you want to find the rth component of your divergence of t, then what you will do, you will take the derivative of this vector with er, because your this component is in the direction of this er. And to find r, what you will simply do is you will simply replace a with er, divergence of t, er equals to divergence of transpose of t. Instead of a we have er minus trace of gradient of er t. Maybe in the definition when we have started divergence of t, where we have written transpose t before and after this, we have gradient of e, that is trace of t into gradient of a vector. And you can also write this thing, trace of transpose of t on left side and this is right side, or this is left side and this is right side, doesn't make any difference, because trace of ab equals to trace of ba. Now we have component of divergence of t, r component, in this form given by equation number 7. So you have to have this component of divergence, we will have to calculate two things on the right side of equation number 7. One is divergence of this, second is trace of this. Let us first calculate divergence of this. You know that t of transpose of er equals to this, the ter equals to trr er plus t theta r e theta, but we have transpose, so trr remains same, but this would be t theta and tr theta instead of t theta due to transpose. Now this is vector, use first component vr, this second component v theta, this. Now we want to only write its trace, divergence. Its divergence would be this. This is from your formula of divergence. This is given by equation number 6. You can write here from equation number 6, where we will use only, instead of vr we will use trr, and v theta we will use tr theta, and you have this divergence of this vector. Now trace of this, before to write the trace we need two things, this tensor and this tensor. You can write er. To find gradient of this er, first we will write er. Er can be written er plus 0 times e theta, and so it means that vr is equal to 1 and v theta is equal to 0. Now use the result from the gradient of vector v. Here v is er and vr is this and v theta is 0. Use this thing in your general result of gradient of vector v. You can write this thing. Now what is transpose? Transpose is simple. Now you have to calculate the product. Here this is del er, gradient of er, and this is transpose. transpose of t, t r r, t theta r, t r theta, t theta theta, and you will multiply these, you will have this thing. What is the trace? Trace is given by this. Now you can use this in your right side of this divergence of t, you can have this thing. Similarly, second component is given by this. You have to calculate this second component. Okay, that how you will calculate this on the similar line as we have which we have followed in the calculation of this component of divergence of t. So you need to follow the same lines, and after some calculation you will be arrived on this right hand side, this form of divergence, second component of divergence of t. Now cylindrical coordinates. In polar coordinates we have basically two coordinates to define a point. Here if you have point P, then it would have three coordinates, r, theta, and third coordinate is z, which will be along the axis. Now, here we have x-axis, here we have y-axis, here we have z-axis. This is P in the space. Now we will take its projection on our xy plane, P dash. In xy plane, components of this projection, which here we are denoting with P dash, components will be r and theta. These are the same components which we have studied for polar coordinates. Simply r with direction er and theta, this position vector which is making angle theta with x-axis, exactly the same as in case of polar coordinates. Now for this r, the second base vector will be perpendicular this er here, e theta. Now what is z? Z is basically vertical height of this P from xy plane, which is given by this z, and direction ez. Now what is this capital R? This capital R is denoting the position vector of this point P. Small r position vector of P dash, capital R position vector of P. What is P dash? P dash is basically the projection of this P on our xy plane. That in cylindrical coordinates, the position vector of point P is determined by three components, r, theta, and z, where r and theta determines the position of P dash. As I was saying that r, theta are the components of P dash on the xy plane, and z determines the height of P, vertical height of P from xy plane. You can easily see from the figure. So what we can say, the cylindrical coordinates is comprised of, not compromised, is comprised, that we can make the cylindrical coordinates with the help of polar coordinates r, theta in xy plane plus a coordinate z perpendicular to that xy plane, to the xy plane. That in this way you can have cylindrical coordinates, r, theta polar coordinates, then third coordinates z. This is simply the perpendicular height from the xy plane of that point P. R is the position vector of point P, so we can write from the figure, simply R is equal to RE. This is R position vector, this is RER, magnitude of RER direction, and this is ZEZ, direction is EZ. So R equals to RER plus Z plus EZ. So what would be its differential? Differential of R is DRER plus RDER plus ZDEZ plus DZEZ. No, this DZ will be 0. DZ will be 0. Why this will be 0? Because EZ never changes its direction. What does this mean? If you have point P here, then direction will be along z-axis. If you have point P here, again the direction will be along z-axis. If you are point P here, again the direction will be along z-axis. So direction of EZ will not change. So it means that there is no, it means that its differential will be equal to no change. So differential will be 0. So we will put here this DRER plus RD theta E theta plus DZ EZ, as we have calculated differential of R in polar coordinates. Now exactly the similar line which we have discussed in finding the all these things for polar coordinates, you have to find those lines and you have to follow those lines and you have to calculate all these things for cylindrical coordinates. Keep in mind that calculation is not given in the book. You have to calculate all these things. This is for your exercise practice. From the exercise you need to do all these things and as your practice. So do these things. Now we will discuss this lecture tomorrow, inshallah. Please go through this thing. Thank you so much.